And then I'll hand over to you, Tim. Thanks for being here today.
Thanks, everyone. Sorry for the slightly provocative title. It's just more fun. Yes, it's 7 a.m. Still drinking my coffee. I'm gonna get, once I get going, it'll be okay. But right now I feel very tired. Okay. So I like to do it this way because it's just like more fun for me to be able to point at stuff and hopefully more engaging. So hopefully it works out. Okay, so I guess the starting point for this talk is that I think that a lot of us have a tendency to talk about memory in a very particular way, and that it's not a coincidence that people, especially people who've never like really thought deeply about the particular issue at stake here, talk this way. It's just how we all, talk about areas of science. And that is that basically, I think in many cases, our mental model, like how does memory work? How should I think about memory? Comes from our own intuitive theories of how the world works. And that one really dominant thing about how our brain treats the world is that it treats it as like a set of like discrete objects. Like my coffee mug either is or is not in my hand. It's just a discrete object that exists, and our brain basically treats the world as made up of separate discrete objects from like really young, right? Even 4-month-old babies are sort of sensitive to this idea. And I think in the history of science, it's sort of classically true that theories that reject the idea that the world is made up of some discrete objects that interact in simple ways are really hard to think through. So like quantum mechanics is a famous example of something that's just like really hard for people to get their mind around. Even Einstein. I think theories of like pressure, like, the fact that, this can expand without any more molecules going in or out of this system, are like really hard for people to understand traditionally in education. And I think the same kind of thing happens in memory research, that like by default, our mental model treats it the same way as like the coffee mug is either in my hand or not, the memory is either in my mind or it's not. And, we use the physical analogy all over the place in memory. So we say, you can hold 3 items in working memory, like you're holding them in your hand. And we say, oh, you're like, how do you retrieve items? Like, how do you search through the bookshelf in your mind for the item, right? And so we use all sorts of physical analogies, and often that's really good, helps scaffold our mental model of how memory works, but sometimes it's misleading. And I think one of the ways it's misleading is this sort of tendency to talk about things as remembered or forgotten in some sort of all or none way. And this is just like incredibly prevalent. This is basically in the vast majority of memory papers. I don't like to pick on other people, so I'll pick on me. So like, for example, here's my most cited paper, which says something like, after seeing 1,000 vivid pictures, observers remembered 992 of them, as though 992 things were in their head and 8 things had fallen out of their head. And, in models of working memory, I'll often see things like people can remember 3 or 4 objects in working memory, or people can hold in mind 3 or 4 objects, like I said, explicitly appealing to this physical analogy, this mental model of how memory works. And it's sort of so pervasive that I don't think people even realize they're using a physical analogy for memory. But I do think it leads us to certain models that I think in the end end up not really being the right way to think about it. And so what I want to do today is just sort of point to a different mental model. Like, I'm not going to try to convince you of everything about how memory works. It would take a lot more than 45 minutes, but just say, like, in general, at least in visual memory, thinking instead of memory not as this sort of physical thing, but instead as analogous to the neural system, instead as analogous to the visual system, effectively having like noisy populations, noisy channels, and a sort of whole hierarchy of those noisy channels as your memory representation. Makes a lot more sense in some ways. It can explain a lot of interesting data. And that's a pretty different kind of analogy. It sort of appeals to neuroscience, but not by using neuroscience methods, just by saying, look, this is like a different way of thinking. And I'll try to show you 2 examples of this way of thinking about it as sort of hierarchical in the second part, and as sort of noisy populations in the first part, and how that's different than the discrete way, the discrete sort of all or none way. We'll start with a standard visual working memory experiment. There are lots of ways we could start, but I got the sense this was a working memory-ish crowd. So I'll give you just an example in case you've never seen it, which is unlikely. So for example, try to hold in mind these 5 colors as best you can. I'll fill these in. Okay, they disappear. And then I probe you on the color by asking you exactly what color was in that spot on this, my favorite color wheel here. So exactly what color was there. It's a hard task. You have to know something pretty precise. So in fact, it was right up there. And if you do this kind of task, what you find is data that looks like this. You find that 0 being exactly on the right spot on the color wheel. There are lots of responses near 0. 180 or negative 180 being clicking green for red, exactly on the wrong side of the wheel. And you tend to find data that looks like this. Lots of responses near 0, but also this sort of long tail of errors. And for many, many years, the classic way of thinking about this has been looking at this and seeing two things going on, seeing that it looks like you could break this up into two components. You could break it up into something that you might call guessing. That is, it looks like sometimes people might just have no idea what the answer is. And if you guess, you're going to have just uniform responses across the whole error distribution. You're going to be equally likely to be 0 and negative 180 away. And also some sort of responses that are based on the target, but just sort of noisy. And then you can measure the precision of memory from these. Probably many of you have run into this. This is like super popular in all sorts of literatures. And in the original working memory literature that this came from, this was used to argue that all items past 3 are lost completely. And that was based on the fact that the precision of memory seems to say about the same when you have 3 items in mind as, say 6, but the guess rate just goes way up. And so that was consistent with the idea that 3 things are in your head and the other 3 things are gone. You dropped those objects. They broke on the floor. And so this is, of course, not just for color. These are just some example wheels we use in my lab for all sorts of different things. I sort of picked color because it's the most popular, but everything I'm going to say applies to equally to orientation and shape and faces. We use all of these domains to do the same kind of task, and you find qualitatively the same kind of data in all of them. And this sort of method of trying to take those kind of psychophysical wheel tasks and fit a model on top that tries to distinguish changes in precision from changes in sort of guess rate, the number of represented items, is just like incredibly popular over the last almost 15 years. And they span all sorts of conclusions in all sorts of literature. So for example, claims that because the attentional blink mostly affects guess rate, that means consciousness is discrete, all or none failures of consciousness, to iconic memory, to working memory, like the claim that how many things you can hold in mind relates to intelligence, but the precision of those things doesn't, all the way through long-term memory, like work by me, claiming that like the precision of working memory and long-term memory is really similar, even though the sort of guess rates are really different, right? And so that's the setup. That's like one particular instantiation of this pretty discrete way of thinking, right? Of like some objects just are lost. You can hold in mind 3. And, this is just like a super important thing. I think the meta thing here is that everybody in the whole world is super happy when you change from being able to measure one thing to 2 things, right? So you used to be able to measure memory performance in a given situation, but the sort of implicit claim here is that no, if you measure it using this task, you can measure 2 things. You can measure precision and how many items are remembered. You've sort of separated memory into its components and can measure them. And so for the last few years, we've been thinking that turned out to be wrong, that even though I was fully on board with this mixture model framework, this 2-component memory idea, I even wrote the toolbox a lot of people use to analyze that kind of data, that it turns out that instead, the answer is different. And so the first thing I want to tell you, sort of substantial thing I want to tell you, is how we've decided to think about this instead, how we think this actually works instead. And the secret is to give up on that really discrete way of thinking, instead to think about memory as sort of made up of continuous strength signals, that some signals are stronger than others. And that amounts to basically signal detection theory, for those of you who are familiar with that. And the other thing that comes into play is sort of how the stimulus space is structured, basically measuring the perceptual structure of your space before you do memory experiments. And that amounts to using psychophysical similarity scaling. So I'll explain those 2 things now. Okay, so here's how you could instead think about that task instead of this discrete failure way. You can start by thinking about just signal detection theory in general. Imagine I encoded a purple color, and then after some delay, so it was sort of hard, I asked you, which did you see, the purple or the green? So standard 2 alternative force choice memory test. The standard signal detection framing of this is that the green one that I didn't see has 0 familiarity, but it's noisy. Sometimes things feel familiar that weren't really there. Sometimes you feel your cell phone vibrate in your pocket, even though it did not vibrate. Like, signals are noisy, perception is noisy, memory is noisy. So there's some sort of noisy familiarity signal where more familiar is towards my head. And purple, because you did see it, got boosted. It got, increased familiarity. And so on average, purple tends to feel more familiar than green. But, on any given trial, you're just getting a noisy sample, and so it might not, right? So on trial 1, it might be that purple feels much more familiar than green. But on trial 2, it might be that, you got green felt really familiar that time and purple felt less familiar. And so you make an error, right? So you probably have all done, norm inverse hits minus norm inverse false alarms or something, where you take performance and convert it to D prime. It's like measure of strength of perception. And so that's basically just acknowledging that there's an axis in your mind of like familiarity, a continuous strength signal for every item that says how strong the memory is. That's what signal detection theory is basically claiming: noisy signals based on a single axis. And so this is like the null hypothesis of memory in many ways. This is like how most people analyze perception data and how a large swath of the memory literature analyzes its data. And the insight of our claim about maybe that's all that's going on even in these more complicated tasks is just to consider what happens if you changed this task from a 2 alternative force choice to a 4 alternative force choice. So imagine I gave you 4 choices afterwards. I said, did you see one of these 2 greens or did you see one of these 2 purples? Which of these 4 did you see? How would you think about that? How would you write that down in this kind of model? Well, what you want to start thinking about is like, well, how much familiarity boost does an item get must in some way depend on how similar it is to the target color. So when you only have the color you actually saw, the target, and then another color that's totally dissimilar, then you're going to get some boost in familiarity for what you saw and no boost for something you didn't see. But imagine that we showed you a color 1 degree on the color wheel away from this light purple. Well, like, it almost has to have the same familiarity boost as that light purple because you literally cannot tell them apart perceptually, right? So it can't be the case that only this color got a familiarity boost and all other colors got none. That like doesn't make sense as a model at all, right? And so instead you end up thinking, well, there must be some sort of structure here. There must be something about similar colors to this that are basically perceptually confusable with it must end up also feeling familiar after you see this color, whereas far away colors must not. And then when you write down that model, you might say, okay, well, so this green color is also really dissimilar. And so it's going to also be centered at 0. And so this is going to be a standard 3 alternative force choice signal detection model. The thing you saw gets a boost of D prime. The 2 things you didn't see are centered at 0. And so they're sort of unlikely to be the most active. But when you think about this dark purple, well, you've got to assume it's going to have some shared familiarity from having seen the light purple. It's going to have some boost in familiarity. And the question is just really how much. And so then you're going to say, well, that distribution is really going to be somewhere up here. It's going to feel pretty familiar to you, even though it's not exactly what you saw. And so it might be very likely to be the most familiar, but, not on every trial, right? And so this is like basically the whole thing. Like, if what you believe when you look at this is people are going to pick that dark purple more often than they're going to pick those greens, then what you're saying is, well, I think that seeing light purple made me get a boost in familiarity for dark purple as well in this kind of framework. And so we said, okay, if that's true, then, what does this function look like? How similar does it have to be? And basically the insight is really just the same thing I said already, which is that, well, something 1 degree away is indistinguishable. So it has to basically get the same boost as the target color. And they must sort of fall off depending on how perceptually overlapping it is to at least some extent, right? And so the idea is, if we could figure out what that function is, then we could model this task as a 360 alternative force choice, right? Now this just has 360 distributions on it, like how familiar is purple, how familiar is purple 250, how familiar is purple 249. And then all we would need to specify that model is what this function looks like. And for many, many reasons that I won't spend a lot of time on here, you would probably guess this is going to be basically an exponential decay as a function of distance. You'd think that because there's just tons of work to suggest that's pretty much always how it works, right? That's basically Fechner's law. It's the universal law of generalization from Roger Shepard. It's GCM model from Nosofsky. There's all sorts of reasons to suspect that's true. There's really deep theoretical reasons why it should be true. Like, for example, neural overlap looks that way. Cells that care about green don't care about, purple or red at all. So there's going to be some long flat part. And so there's going to be all sorts of theoretical reasons why that's true. In our data, we basically just measure this in a perceptual task. We just say, sort of how confusable are these colors in a perceptual task, and we map that function out perceptually. And we say, okay, now we understand the stimulus space in perceptual task. Let's just say that's this color space, looks like that. That's how confusable things in this color space are. And we keep that fixed across all conditions, all participants. It's just like a property of the color space is what we act like is true. Probably not perfectly true. So once you have that idea that seeing light purple is going to activate other colors that are perceptually confusable with it, then when you write down this signal detection model, you end up, as I said, with 360 distributions. It's not very pretty. Well, it's kind of beautiful, but it's not very understandable when you just look at it quickly. So all the colors that are really far away that are not similar to purple at all are just centered at 0, just like that original green one. Purple, the light purple color is still centered at, D prime 2. And in between, you have this gradient where really similar colors also get boosted. And we're just sort of using this confusability in perception to figure out where those go. And so the idea is, what if this is all that was happening, basically? Well, when D prime is really high, you're basically only ever going to get the winning color coming from one of the ones that got boosted really a lot. When D prime is really low, though, all these 360 distributions are going to be pretty much on top of each other, and you might pick any one. They might all be the winning one. So on a given trial, purple might feel the most familiar, or maybe green might feel the most familiar once you just draw a noisy sample from these. So this is basically just like almost exactly just the extension of signal detection theory to 360 alternative force choice, but with like slight added wrinkle that, of course, there's going to be some perceptual confusability if you use continuous spaces. And so you have to sort of build that into your model a little bit. Okay, so here's another way of thinking about that, because I think people find 360 normal distributions hard to understand, which is before you see anything, your familiarity is at 0 for all the color channels. When you see this green color, it boosts green's familiarity, but it also boosts similar colors' familiarity according to that fixed function we measure in a perceptual task in independent observers. That's just the color wheel, confusion function. Then during the delay, these signals are corrupted by noise, right? So like each channel here gets corrupted by normally distributed noise. And so at the end, what your memory looks like is this entire distribution of activation of every channel. And I say, hey, which one is the highest? And you say this green one, and that's your error. So it's basically the model here is just, if once you have this function, it's just what if we added noise to it and picked the best one? That's the whole model. That's signal detection theory in a force choice task, right? Add noise and pick one, pick the highest one. This way looks kind of beautiful. Okay, so what does this predict? Well, if the signal is very weak and the noise is very strong, well, then which one of these is the highest is going to be totally unrelated to the target color, and you're going to end up with a uniform distribution. If the signal is sort of moderate and the noise is sort of moderate, well, then the ones in the middle are going to be a little bit more likely to win because, of course, they got a little signal boost. But of course, every once in a while, you're going to get a really strong peak of the noise outside of where the signal was, and so you're going to end up picking something really far away from the right answer. By the time you get down here where your signal's really strong and your noise is really weak, then of course you're basically never going to pick anything that's not from the center-ish part of this distribution because the signal's so strong. It's nothing else is going to ever be the highest, and you're going to get a distribution that looks like this. And so this is basically the claim of like, what if you just took seriously the idea of continuous memory strength signals and noisy decisions? And we call this the target confusability competition model, TCC. It's not the best name, but it is what it is. Naming stuff's hard. And the basic prediction here is that, sort of in contrast to what I said at the beginning, where people often look at these distributions and they see two or actually often three separate parameters, like the guess rate, the precision, and sometimes variability in precision, that instead the prediction here is that once you fix the color wheel, like once you use a single perceptual space and measure it, there's just only one knob here, right? There's like bad performance, low signal to noise, all the way up to high performance, high signal to noise, high D prime. And so that's a pretty strongly contrasting prediction with the way a lot of people think about this, including me. And so to test that, we've basically done, I don't know, at this point, like more than 60 experiments, I think, looking for whether this is always true or whether you do sometimes end up not where this model predicts. And we just always find this model fits the data no matter what you do, basically. So here's an example. When you have one item in mind, here I'm just plotting the absolute value of errors. These are symmetric distributions. So we just fold them over on each other and plot the absolute value so we can fit more things in short papers. That's basically why. So when you're one item in mind, you get a really strong signal and you get a high D prime. And so you only make errors to really similar colors. By the time you get down to 8 items in mind, you get really weak signals from all 8 items, and probably more noise accumulates during the delay. In general, your signal to noise drops and you end up with a really long tail. And just changing D prime in this model, just saying, what if all the items were encoded sort of equally well, but they each accumulated independent noise, the same amount of independent noise, fits the data basically perfectly as a function of set size. Didn't have to, could have been that there's like excess guessing here. And in the paper, we show pretty clearly there's not. Also, if you change encoding time, if you give people more time, then it looks like they get more signal and the signal to noise ratio goes up. And that's true at all the set sizes. And again, all of these are well fit by this model, better than they're fit by the mixture model approach. If you increase the delay, D prime drops, more noise accumulates from the same signal. And so in all of these cases, we have I think I just showed you 22 different plots where it could have been that with one knob, just signal to noise ratio, you couldn't fit all those plots. If there were really 2 or 3 different ways these distributions could change, what's the chance that just one knob would fit every single manipulation I just showed you, right? And so that's true in color. It's also true for orientation. You measure a different similarity function because it's a different stimulus space with different perceptual confusion properties. And it's for faces, you can measure another perceptual confusability function. And every case, these independent, the perceptual confusability structure for faces predicts the error structure for faces. But, the color one doesn't predict the error structure for faces, right? So something about just this perceptual structure plus noise seems to explain this data really well. And so, unfortunately, there's like a negative point here, which is I think basically all of these dissociations are illusory, unfortunately, these 1,000 papers dissociating these things. And I think that they come from, including mine, right? I think that it's basically a function of some tricky nonlinearities that make you think you're measuring 2 things. Here's a way to plot that in a way that hopefully makes sense to you. What I'm doing here is taking all of our data that's in that paper. So each one of these is an experiment, and plotting the guess rate from the mixture model and the standard deviation from the mixture model against each other. So this is, what if I fit that data set with a mixture model and I plot its guess rate and its standard deviation. And what I'm having this dashed line is what this TCC model says is the only thing that can ever happen. It says this is basically the only regime you can ever have because there's really just one parameter. These are weak memories and these are strong memories. And there's not really 2 different things going on here. There's just a nonlinearity. And so what you end up with is predicting that, all those papers that find guess rate changes but precision doesn't are going to be in regimes where memory is weak. Because over here, it's a steep function. Over here, you're going to end up with a change in standard deviation from 22 to 23 and a guess rate change of 0.25 to 0.5. And so you're going to only find a significant difference in guess rate and not standard deviation. And so in domains where people are studying weak memories, they're going to find only guess rate changes sometimes. And over here, you're going to find that only precision changes and the guess rate stays the same if you're studying strong memories. And people who happen to be studying sort of in between memories are going to find both change. But in reality, there's just one knob here. There's just one parameter, just signal strength. And this seems to hold up. We've now reanalyzed a huge swath of the data from those dissociations. What I thought were the most compelling dissociations, we basically went and reanalyzed. We have a whole swath of papers we're about to preprint that do this, and none of these dissociations seem to hold up. They all are better fit by just assuming the signal to noise ratio changes. Okay, so that's the first part here, which is like, instead of thinking of memories as sort of failing, if you instead think there's some non-linearity in terms of how confusable stimuli are with each other on that wheel. We should have probably known a circle wouldn't be linear, but for some reason that wasn't obvious. I'm not sure why. There's some non-linearity in how confusable each item is with the target. And then memory decisions are made by basically having a competition among continuous strength signals and picking the maximum. Then, hence target confusability competition model, then that can explain all of that data. And I have a ton of other experiments I can talk about if people are interested. But the basic summary here is that thinking about both working memory and long-term memory, and thinking about these kinds of decisions, I'll show you in a second, the long-term memory version, as basically noisy decision-making where memories just differ in a strength axis, explains a lot. The structure of the response distribution comes from noise and a fixed stimulus similarity function. And there's no discrete failures here, right? Instead, it's just saying everything you see causes neural activity. And some of those things accumulate noise faster than others. And when I probe you, you just look at the population you have in your cortex or whatever. And that is how you make your response. So instead of saying somehow this thing was processed in V1, but half a second later it's just completely gone, you just say, well, some things are accumulating noise faster than others. When you're trying to protect those representations with attention in a working memory task, it's harder when there's more things to protect, and so they accumulate more noise. And we did like a million things because, of course, trying to tell everyone they're wrong about everything needs a lot of experiments. So we've done this with all sorts of questions about variable precision, long-term memory, confidence reports, encoding time delay, et cetera, et cetera. And I showed color, but we've also done face identity, orientation, shape, like I said at the beginning. Okay, so that's the first idea of the two ideas that I hope to talk about. So that's the first idea, that like thinking about it as sort of noisy channels. You'll notice that like in this model, I should have put a slide with this. In this model, you've got like an activation level for every color is like your memory, right? So your memory isn't just, I think it's green. Your memory is how active is every single color channel. And there's something really profound there that I cut out of the talk, which is like, can you find evidence that people really have a full distribution of activation values for each color? And yeah, we have some evidence favoring that idea, that they don't just think it's green right now, they have some activation value for everything. This is like the population noisy channels view. The second thing that I think also sort of doesn't match our intuition is that memories are really hierarchical in the same way the visual system is, sort of within objects, which I won't talk about today, but also across objects, that we're using sort of a whole set of structures at many levels of abstraction to make judgments about any individual object. And I usually talk about this in working memory, but I decided that it would be nice to showcase that the same phenomena hold across all visual memory tasks, basically. So I'm going to switch to long-term memory recollection in a second. What do I mean by hierarchical structure? Well, the way I was just talking is that when you see 6 colors, they each get 6 different noisy distributions of activation. I rotated them sideways to fit them here. So for example, for this one, you think, bluish purple is the most active color, but for this one, you also think bluish purple, even though it was orange. And that's like the mental framework I just set up. But in reality, it's sort of unlikely people basically have 6 independent representations that don't interact in any way in their decision, right? People are really using something like a gist or an ensemble of the items in working memory and long-term memory tasks, right? They're grouping across items in all sorts of ways. And so their memory is never going to be just one feature from one item with one set of noisy channels. And so I want to do next is talk about that. How do people use this kind of gist, and how does that change how we should think about memory? And yeah, the case study I'll use is recollection and long-term memory tasks. So it turns out you can use exactly the same kind of task to study long-term memory as working memory. You can't obviously show people 100 colored dots and then ask them what the 43rd dot was. But what you can do is create a huge stimulus set, which is what I did in my postdoc, of objects that you can color rotate. And so you can have, for example, what color was the notebook or what color was the backpack. And now you could show people many, many objects and ask them to report the color of a given object and ask what happens. And so you could basically do exactly the same task, but now, hey, what color was this couch you saw? And when you do that, it is no surprise, I guess, that you end up with error distributions that look exactly the same they look in working memory. You end up with this sort of long, fat tail of errors that you could interpret in a mixture model framework. And in fact, many people have, right? So people have often claimed that again, the right way to think about this is a mixture model, and that means sometimes you completely fail to find the object in your mind, that physical analogy, right? Sometimes you can't find it, and so you have just guess randomly. And I already mentioned this when I showed you that summary slide, but of course the same TCC model fits this data perfectly well, with no failures here. Just saying that despite this long tail of errors, this is just what happens when D prime drops and you have a nonlinear perceptual space. And so we have a whole paper that, if you're interested in this, we have a long-term memory paper that's sort of about this issue, about this model and long-term memory, and how strong long-term memory can be and how working memory and long-term memory relate. Okay, so that's the idea. In long-term memory tasks, you can do the same kind of thing. And then what about sort of hierarchy? Well, of course, you can have really spatial hierarchy situations. So like the books on a bookshelf are not going to be independently encoded. You're going to obviously like use the bookshelf structure itself to help encode each book. But you can also do the same thing in sequence tasks. So we made a stimulus set where we have not just like one chair, but many chairs, all of which we can color rotate, and many lamps, all of which we can color rotate. And so then we can create stimuli sets where we have, all the lamps in all the colors, and we can ask people to remember those and ask how the structure of the set influences their memory for individuals. So this is a paper that is never going to get published, but has been a preprint since 2018, because it turns out things I am first author on never get done because I only work on things for my students. But it's a pretty much full paper. We just never got through the publication process. Okay, so here's an example task that we did in that paper. Try to remember the colors of each of these objects. Okay, is this one of the objects you saw? Yes or no? And if it was, what color was it? That's the task. And so the kind of data you get out of this is pretty cool, actually. So you get data from items they actually did see. So that was an item you saw, for the record, although there was not a lot of nodding. You get, for items you did see, you get a distribution of which colors they report for that item. And for colors they did see, you get a distribution of items they report. And of course, these are going to be different for different items that were in different colors. But you also get, for items they didn't see, but they said they saw. So I said I saw this, but I was wrong. And I get to know what color you thought it was. And that's pretty cool, because that's a measure of what you thought airplanes in general were sort of like, as opposed to any specific airplane, because this is not an airplane you saw, right? And the dominant models of what goes on in a task like this, like why do we false alarm to new airplanes, is, for example, models of the famous DRM task where you false alarm to sleep when you didn't really hear the word sleep, you just heard sleep related words, is often something like fuzzy trace theory, where Well, you have in your mind that airplanes in general were sort of green and blue. And you also have in your mind that this airplane was this color and this airplane was this color, but some of them failed. You don't have all the airplanes. So when you don't have it, you just sort of guess on its color based on what airplanes were like in general, right? That's basically the same framework as the mixture model framework, but here framed in fuzzy trace theory and long-term memory. This kind of model is just basically everywhere. And an alternative way of thinking about this looks more like this. It says, well, you have the knowledge that airplanes were sort of green-blue, and you have noisy knowledge about the airplanes in general. And when I ask you about the color of any specific airplane, you might just rely on all of this. Your memory trace in some way is all of this information at once, not just like if I don't know it, then I use the gist, but instead, how do I use all of this together? For a long time now in working memory, we've been talking about it in terms of what would be true if it was hierarchical in that way. And the most obvious prediction you get is that you should get systematic distortion towards the category, even for well-remembered items. This turns out to just be Bayesian optimal if you have sort of a hierarchical structure in your mind. So for example, imagine you knew that airplanes in general were sort of approximately greenish blue, and you think you saw an airplane that was sort of yellowish green, but it's noisy. You're not precisely sure exactly which color you saw because memory is noisy, as we just saw. Well, if that's true, what you should do, if you were going to rely on both kinds of information at once, if you were going to really use the hierarchical structure, is you should respond somewhere over here. And that's because it's much more likely you made an error and thought it was yellower than it was, than that you made an error that thought it was greener than it was. Because most of the airplanes were sort of greenish, right? And so it's much more likely your error was sort of in by going too far that way than by going too far that way. And so if you basically integrate this, you end up with this Q combination situation, and you end up putting there. And so the question is like, do people do this? Like, even when they're very sure about the memory of an item, do they nonetheless get distorted towards the category? That would be evidence they're really always relying on all sorts of hierarchical information. And this task lets us ask that pretty nicely because, well, it turns out that this is basically what would happen if you had no item information at all, right? If you had never seen this item, we know what colors you would report. This is basically what your guessing distribution looks like. This is like an empirical measure of guessing. And so we can then ask, you know, do these look like a mixture between exactly the right color and guessing? Or do they instead look like they're sort of distorted towards the category, but not just because of mixing and guessing? Does that make sense? It's a cool task for that reason. And so we basically can take people's errors. Imagine this is the center color of the bell category, and we can separate by the items that truly were clockwise or truly were counterclockwise. And we can look at their errors. And items that were counterclockwise of the actual category center, people in general tend to make errors towards the category. Items that were generally clockwise, so items that were really bluer than the category in general was, they tend to make errors towards the category, so, you know, counterclockwise. So there's this general effect where people do this, and the modeling question here is like, well, is that only because they're mixing and guessing, or is that because they're really distorting their actual individual memories? And so we can take these two distributions and we can just flip them over and average them together and say, look, in general, people make errors towards the category. And then we can try to ask, is that because there's a mixture of guessing and accurate item reports, like in fuzzy trace theory, for example, or is that because people are really truly integrating the two sources of information all the time? And the modeling here is a little complicated, but effectively, we have access to what would happen if people were only guessing using the gist, because we have those airplanes they didn't see. So we can take that red line here and sort of make it as high as possible. Say, what if all of the distortion came from just guessing that way? And then subtract those two and say, oh, yeah, I already had that. And subtract those two and say, well, what would be left? What if we just assume that all the distortion came from guessing? What would be left? And it turns out it's still really biased. So even if you presume that a lot of the time people are purely guessing based on what they knew about airplanes, it's still really biased towards the category, even in what's left over. And so, for example, 58% of the responses are still towards the category, even after filtering out as many possible things that are sort of pure guesses based on the category as possible. And so we think this is, with a little bit more modeling than I had time to show you, evidence that there really is a sort of distortion of individual memories away from what really was the center of that item towards the category. And this turns out to be true even if you ask people their confidence. So even if you show people, for example, an airplane, and you say, did you remember this? And they say yes. And you say, how well did you remember this? And they say the highest confidence level. And then they report a color, and then we ask them their confidence, and they say they're very confident in that color report. They're still biased towards the category on those items. So this is not just guessing. This is really the fact that individual item memories are really distorted towards the category in all situations. And this is basically evidence for these hierarchical memory representations, that even true and accurate memories seem to be distorted by this gist knowledge of what airplanes were like in general. There's some cool implications here. I mean, they're not so different than what a lot of people have said who think this way, this hierarchical Bayesian way. But one implication here is that false memory really ends up just on a continuum with true memory, right? So if you have a pretty precise item memory, like you're pretty sure it was in this range here, then the optimal thing to do is to give a lot of weight to the item memory and a little bit of weight to the category, and give a response like that. You get 80% item, 20% gist in your response. If your item memory is super, super precise, then you should basically ignore the gist and put 95% of your weight on the item. That's the optimal thing to do. If your item memory is really noisy, then you end up putting most of the weight on what airplanes were like in general. And you end up really distorted towards the category. And of course, the wider and wider this gets, in the limit, you just end up in a place where you have no idea about the item at all. And so you just only use the category, right? And so this is like, as opposed to thinking sometimes people use the gist of the category and sometimes they use item information. Instead, it's just saying, well, what if you just combined them optimally at all times and memories were noisy, right? Then you'd end up somewhere in between in a lot of situations. And this is, puts false memory on this continuum with true memory. Okay, so that's the end of the talk. So the idea here is that when I ask you to remember what color this was in the context of a task like this, instead of you thinking it's green with a little just exact green in your mind, instead something more like this is going on. You've got like some noisy activation of each color for what color that was, but you've also got information about what in this task these airplanes were, and in general what the colors in this task or this trial were, and you're basically combining all of these sources of noisy channels together. And as I said at the beginning, hopefully this reminds you of like a visual system, right? There's like noisy populations in a hierarchy. So I'll just foreshadow one cool thing, which is, of course, you can take convolutional neural networks here, visualized here, which are noisy populations in a hierarchy, and ask, do they look like this, and can they model memory in simple ways? And it turns out, for example, that an object-trained convnet, a CNN, the similarity as a function of distance in color space looks exactly like human similarity for colors, for example. You get the same exponential fall off, and adding noise to these representations and choosing the best match gives you the error distributions you get in working memory and long-term memory tasks, right? So there's like some clear links between hierarchical noisy representations and the visual system is like the idea I'm trying to convey here. Okay, so overall, I did recollection of visual working memory. I talked about color report for both just because you can't explain too many different things in one talk, but it's not all limited to that. And the goal is to push against this extremely strong desire to talk in terms of discrete items that are either there or not there, and instead think of memory as this sort of noisy channels, hierarchical structure mental model as helpful. And of course, the specific thing I try to argue is that these are not really discrete failures, even the ones in the mixture model framework that look like it, but just basically the natural outcome of a model that has continuous evidence and noisy decisions. And finally, that even really well-remembered items are influenced by high-level knowledge, like just that memory is deeply hierarchical across items and within items. And thank you to my lab and my funding and everything like that.